They thought it would be simple. When German engineers recovered the wreckage of a downed P-47 Thunderbolt, they expected to find ordinary American machinery, heavy, rugged, predictable. Instead, they uncovered something that left them frozen around the workbench. The turbocharger inside the Thunderbolt wasn't just advanced, it was beyond anything the Reich could build in 1943. Every blade, every alloy, every curve of metal told the same story. The United States had achieved an industrial breakthrough Germany could not match. And when the engineers finally opened the turbo's core, they realized the truth. This wasn't a machine. It was a warning. In the early summer of 1943, deep in the forests of Western Germany, a dull metallic glow rose between the trees. A small team of German recovery personnel, soldiers, mechanics, and 2 Luftwaffe engineers picked their way through the underbrush, guided by the smell of burnt oil and the distant crackle of cooling metal. Hours earlier, villagers had reported the roar of aircraft engines overhead, followed by a violent explosion and a trail of black smoke spiraling down toward the valley. By the time the search team reached the crash site, nothing remained intact except a few twisted fragments of aluminum and the unmistakable bulk of an American Pratt & Whitney R2800 radial engine lying half buried in the earth. What the Germans didn't know yet was that this particular wreckage would become one of the most closely studied pieces of American technology to fall into their hands during the war. And at the center of it all was a device they had long suspected, long envied, and long failed to understand: the General Electric turbocharger used on the P-47 Thunderbolt. To American audiences today, the P-47 is remembered as a powerhouse, rugged, heavy, and nearly indestructible. It could absorb damage that would tear lesser machines to pieces. But to wartime Germany, it was something far more troubling. Reports from pilots on the Western Front kept repeating the same observation. The Thunderbolt climbed too well, dove too hard, and retained far too much power at altitudes where most fighters, Allied or Axis, began to gasp for air. Something was giving the P-47 an advantage in the thin, freezing altitudes above 25,000 feet, and the Germans were determined to find out what it was. As the 2 Luftwaffe engineers approached the wreckage, they recognized it immediately. "Thunderbolt," one of them muttered, brushing soot from a bent cowling plate. The radial engine was enormous, even mangled and cracked open from impact. But behind it, scattered in pieces across a 10-yard radius, they found what truly caught their attention: sections of piping, oddly shaped housings, and fragments of turbine blades that, to the trained eye, did not belong to any supercharger the Germans themselves had used. They had found, for the first time in months, the remains of a complete American turbocharger system. Within hours, military trucks arrived. The wreckage was collected piece by piece, carefully packed into crates marked Flugmotor Spezial. It was then transported to a Luftwaffe technical evaluation center outside Berlin. This crash recovery was not unusual. What was unusual was the urgency. The Thunderbolt's performance had long been a puzzle for German analysts, and now, at last, they had a specimen to study. In the days that followed, the fragments were laid out across a long steel table inside a cold, dimly lit workshop. German engineers, experts in precision mechanics, metallurgy, and aircraft design, bent over the pieces with magnifiers and notebooks. They had reverse-engineered many Allied components before. They expected this to be no different. After all, German engineering was world-renowned. If the Americans could design a turbocharger, surely the Reich could match it. What they did not yet understand was that this turbocharger represented something far greater than a piece of machinery. It represented the industrial might of the United States, its factories, its access to high-grade materials, and its ability to mass-produce components of unbelievable complexity. For the Germans, It would soon become clear that the true challenge wasn't design, it was capability. In American wartime factories, thousands of workers built turbochargers with precision tools, exotic heat-resistant alloys, and manufacturing methods ahead of anything Germany could sustain by 1943. The turbocharger was more than a performance booster. It was a symbol of American engineering power, fueled by an industrial base untouched by bombing and supplied by near-limitless natural resources. But the Germans, at that moment in 1943, still believed it could be copied, still believed that by studying it closely enough, they might reclaim the high-altitude advantage they were steadily losing to the Allies. Back in Berlin, the engineers began reconstructing the turbo as best they could. They arranged each fragment like pieces of an archaeological find. Even in its shattered state, the turbocharger's purpose was obvious: to compress thin air at altitude, feed it into the engine, and deliver enormous horsepower far above the clouds. The Germans already used superchargers, but the American system was something else entirely. A supercharger robbed power from the engine. A turbocharger fed it more power without the same penalties. For American aircraft, especially the P-47, this meant climbing faster, flying farther, and escorting bombers across Germany with brutal reliability. To understand this, the Germans needed to see inside, to open a complete turbo unit, not just fragments. And as fate would have it, less than 2 weeks after the first crash, another P-47 went down intact enough for proper analysis. This time, the turbocharger could be removed in one piece. It was that moment, the lifting of the intact turbo onto the steel workbench, that marked the beginning of a revelation the Luftwaffe had not expected. They still believed imitation was possible. They still believed the Americans had simply scaled up existing designs, but when they finally opened the casing, everything changed. When the intact turbocharger from the second downed P-47 finally arrived at the Luftwaffe's Technical Evaluation Center, it was treated with a level of seriousness usually reserved for secret weapons. The device, roughly the size of a large steel kettle but far heavier, was lifted onto a reinforced workbench under high white lamps. Around it stood 6 of Germany's top engineers, summoned from factories and research units across the Reich. They believed that what lay inside the housing could change the course of the air war, or at least slow the Allied momentum that was beginning to tilt against them. At this point in the war, Germany still possessed some of the most respected aviation engineers in the world. The Daimler-Benz inline engines powering the Messerschmitt Bf 109 were elegant and highly efficient. The BMW 801 radial engine that drove the FW 190 was robust and cleverly designed. German tanks, rockets, and early jet aircraft demonstrated a high level of mechanical sophistication. For these engineers, it was only logical to assume that any American device, even a turbocharger, could be understood and copied with enough patience and technical skill. The plan they laid out was ambitious, but not unusual for wartime Germany. First, they would conduct a complete disassembly of the turbocharger. Every bolt, every rotor blade, every housing section would be removed, drawn, measured, and weighed. Specialized microscopes would be used to examine the metallurgy. Chemical tests would determine what metals and alloys were used. Once all components were documented, a second team would attempt to model the system mathematically: airflow, thermal expansion, mechanical loads, and pressure curves at altitude. The third stage, if all went well, would be a prototype built with German materials and machining techniques. To the engineers present, it seemed realistic. After all, they had reverse-engineered British radar, American bomb sights, and even captured P-51 Mustangs. Why not a turbocharger? They began the disassembly with practiced confidence. The first surprise arrived almost immediately. When the external bolts were removed, the engineers noticed the threads were cut with a precision they had difficulty matching, even in their best factories. The steel casings were cast using techniques unfamiliar to them, smooth on the outside, but internally reinforced by a complex web of metal ribs. The Americans weren't just manufacturing, they were mass manufacturing engineering solutions that Germany, under constant bombing, could barely produce even experimentally. Still, they pressed on. As the turbine housing came apart, the core of the device was revealed. The turbine wheel and compressor wheel, two pieces of metal that, despite being scorched from impact, still showed signs of extraordinary craftsmanship. The turbine blades were thin, curved, and perfectly uniform. Even more troubling was the type of alloy used. It resisted deformation even under heat and impact. Several German tests showed that the metal was significantly more heat-resistant than equivalent alloys available in the Reich. The Americans were not simply using a turbocharger, they were using an advanced turbocharger built from materials scarce or inaccessible to wartime Germany. The engineers exchanged concerned glances. For the first time, they began to understand the scale of the challenge. But the problems didn't end there. The turbocharger itself was only part of the system. The P-47 used a long and intricate network of exhaust pipes, some nearly 8 feet in length, that carried hot gases from the engine back to the rear-mounted turbocharger. These pipes were not simple steel tubes. They required precision welding, smooth internal surfaces, and consistent curvature to maintain optimal airflow. The Germans sketched the pieces, measured diameters, and calculated temperatures. The more they studied, the clearer the problem became. Germany lacked not the intelligence, but the industrial capacity necessary to replicate such a system in wartime conditions. Across the ocean, American factories, untouched by enemy bombing and powered by thousands of skilled workers, were producing turbochargers in quantities the Germans could not match. The United States had access to strategic materials like chromium, molybdenum, and nickel, essential for high-temperature alloys. Germany, blockaded and running short on critical resources, could not produce metallurgy on this scale. Their own attempts to build turbochargers earlier in the war had already failed due to cracking, warping, or catastrophic overheating. Now, the Americans had solved these problems on an industrial level. Still, the Luftwaffe team continued their work. They believed that if they could just understand every component, perhaps a simplified version could be developed. One engineer proposed removing the long ductwork entirely, replacing it with a compact turbocharger mounted directly near the engine. Another suggested combining the turbo with an existing mechanical supercharger. But each idea ran into the same wall. Germany simply could not build the critical components without the right metal, the right factories, and the right scale of production. A growing sense of frustration filled the workshop. "These tolerances," one engineer reportedly said, tapping a turbine blade with the dull end of a pencil, "we would need months just to attempt a prototype. And the materials, where would we get them?" Another disagreed, insisting that Germany must have the capability somewhere. But beneath the surface, the reality was beginning to settle in. The Americans had not just outdesigned them, they had outproduced them. The turbocharger was the product of a nation whose industrial power far exceeded what the Reich could muster under constant bombardment and diminishing resources. By the end of the week, the engineers had completed their disassembly. They had the measurements, the drawings, the chemical compositions, but they also had a sobering understanding. The problem was no longer engineering, it was impossibility. And yet, they had not even opened the most revealing part of the device. That moment, when they examined the interior of the rotor housing under full light, was still to come, and it would change their conclusions forever. When the German engineers began examining the rotor housing of the P-47 turbocharger, the heart of the entire system, they expected complexity, of course. Every aircraft component had its intricacies. But they also expected the same fundamental principles they had seen in their own superchargers and early turbo experiments: a rotor, a shaft, a bearing assembly, and predictable metallurgy. Instead, what they found inside the General Electric turbocharger stunned them into silence. The first engineer to lift the rotor assembly paused the moment he saw it. He held it under the bright shop lights, slowly rotating it in his hands. It was scorched from the crash, pitted with small impact marks, yet the blades maintained their shape. To the German experts, this made no sense. Even their best heat-resistant alloys would warp or crumble under the same temperatures. This rotor had survived not only high-altitude combat, but also a catastrophic crash and a fiery impact. They began taking photographs, black and white documentation using Leica cameras, capturing every angle. Several engineers took turns measuring each blade with micrometers. What they discovered was unsettling. The tolerances were unbelievably tight. The blades varied by fractions of a millimeter, each one nearly identical to the next. The Americans had achieved a level of manufacturing precision that the Germans could not sustain in the middle of a war. One engineer finally muttered what others had already begun to suspect: "We cannot make this. Die." But they continued working, moving deeper into the assembly. The bearing system was next. The Germans expected some form of ball bearing or a crude pressure-lubricated assembly. What they found instead were heat-treated components machined so precisely that when cleaned of soot, they spun freely with almost no friction. The parts were engineered to withstand extreme rotational speeds, tens of thousands of revolutions per minute, far beyond what German turbo experiments had reached without catastrophic failure. The rotor shaft itself, a simple-looking cylinder at first glance, was revealed under magnification to be crafted from a nickel-based alloy that Germany could not produce in quantity. This discovery marked a turning point. Germany had nickel shortages from the very beginning of the war. Under Allied blockades, acquiring even small quantities became nearly impossible. The Americans, meanwhile, had used nickel alloy in a device they produced by the thousands. This wasn't just engineering superiority, it was resource superiority. As they continued, the engineers moved to the inner surfaces of the turbine housing. The Americans had coat-treated the interior with a method the Germans could not replicate, an erosion-resistant layer designed to minimize loss of efficiency at high heat. The coating itself became a subject of debate. Some argued it was a chromium-based compound. Others insisted it was a proprietary alloy. Testing later suggested a combination of materials that Germany had no capacity to produce in the quantities required. One engineer, shaking his head, said aloud, "This is not a machine built for a prototype. This is a machine built for a factory." The distinction mattered. Germany had engineers capable of producing brilliant one-off designs, rockets, experimental jets, guided bombs, but mass production was their weakness. The United States, by contrast, had mastered the art of building complex machinery at scale. The turbocharger evidence laid that truth bare, but there was still more to uncover. The Germans turned their attention to the exhaust flow passages, the carefully curved ducts inside the turbocharger that directed hot gases onto the turbine blades. These passages were smooth, polished, and shaped according to aerodynamic principles that few Germans had ever applied to internal turbine geometry. Their own turbo experiments often failed due to uneven expansion, turbulence, or cracks forming in improperly shaped ducts. The Americans, it seemed, had solved each of these problems systematically. Next came the heat shielding. While German engines used metal baffles and heat-resistant fabrics, the turbocharger included a multi-layer shielding system made of staggered alloys. It was designed to protect nearby aircraft components from radiant heat, especially in the cramped rear fuselage of the P-47. Germany lacked the industrial infrastructure to produce such shielding, especially in wartime. Their factories were struggling to keep up with basic aircraft production, let alone advanced heat management technologies. One of the engineers, a veteran of earlier turbo attempts in Germany, became visibly frustrated. He knew the Luftwaffe had tried to develop turbo-supercharged engines early in the war. The Messerschmitt Bf-109 and the Focke-Wulf Fw-190 both saw experiments, but every project failed due to overheating, warping turbines, or metal fatigue. Germany had turned instead to mechanical superchargers, which were easier to produce but less capable above 25,000 feet. Now, with the P-47 turbocharger on their workbench, the reason for those failures became painfully clear. The Americans weren't just using better metal, they were using the right metal, in the right shape, produced by the right factories, in the right quantities, with the right tools. The more the Germans inspected, the more they realized how far behind they truly were. Finally, after hours of disassembly, comparison, and note-taking, the chief engineer leaned back and said the conclusion none of them wanted to acknowledge. "This is not possible for us. Not now. Not in this war." It was an admission that Germany lacked the industrial strength to compete with American high-altitude engineering. The P-47's advantage was not a trick, not a lucky design choice. It was the inevitable result of massive industrial capability, scientific expertise, and unlimited access to strategic materials. And yet, there was still one more revelation waiting for them. It wasn't just the turbocharger, it was everything surrounding it, the pipes, the valves, the airflow system, the installation itself. When they studied these components, the final truth became undeniable, and it went far beyond the turbocharger alone. As the German engineering team moved beyond the turbocharger itself and into the larger system that powered the P-47 Thunderbolt at high altitude, a new realization began to take shape. One far more unsettling than anything they had encountered inside the turbine housing. It wasn't just the turbocharger that made the Thunderbolt formidable, it was everything around it. The precision welding, the seamless ductwork, the heat shielding, the mounting brackets, the pressure regulators, the wastegate mechanism, every component worked together in a harmony that no German factory, under the conditions of 1943, could ever hope to replicate. Piece by piece, the engineers studied the full installation. The P-47's turbocharger, unlike most turbo systems in the world at that time, wasn't mounted near the engine. Instead, it sat far back in the aircraft's fuselage, beneath the cockpit and behind the oil coolers. This placement was intentional. It helped with cooling, maintenance, and allowed the massive radial engine to breathe freely without losing pressure at altitude. But it also created a stunningly complex logistical challenge. Extremely long exhaust pipes needed to run from the front-mounted R2800 engine all the way to the rear-mounted turbocharger. Those pipes had to carry scorching exhaust gases at speeds and temperatures few metals could survive. The Germans knew this. They had tried it, and they had failed. They measured one of the bent pipes recovered from the wreckage. It was nearly 8 feet long, flared at specific points to smooth airflow, and had a polished inner surface that resisted heat erosion. The German team immediately suspected a special alloy. Tests later confirmed their fears. The Americans were using high chromium, high molybdenum steel blends that Germany could no longer produce reliably. These metals were strategic. The US had abundant access. Germany did not. Resource scarcity had already crippled multiple German engine programs. Nickel was rationed, chromium shipments had dwindled. Tungsten was confined to armor-piercing ammunition. The idea of building a turbo system requiring large amounts of exotic metals was in practice impossible for the Reich. And yet, here was proof that the United States was manufacturing thousands of them every month. The next component to catch the Germans' attention was the wastegate system. On the P-47, the wastegate regulated how much exhaust entered the turbocharger. Too much pressure and the turbine would overspin. Too little and the supercharging effect would weaken. American wastegates were driven by precise temperature-resistant actuators connected to a network of sensors and hydraulic lines. It was a system of moving parts that adjusted itself during flight, based on the pilot's throttle input. German wastegate designs were rudimentary in comparison. Their actuators frequently seized under heat. Precision valves broke down. Their systems lacked the finesse required for altitude stability. On paper, the Germans understood how a wastegate should work. But the American implementation wasn't theoretical, it was industrial. Everything the United States built, it could reproduce in tens of thousands of units. The Germans, increasingly aware of this, shifted their analysis. They no longer asked, "How does this work?" They asked, "How do the Americans build this in such quantity?" The answer, as they eventually documented, lay in a combination of factors that Germany could no longer match. Untouched industrial infrastructure, unlimited access to natural resources, and mass production techniques refined long before the war even began. American factories had perfected interchangeable parts. Their machining equipment was automated. Their tools were standardized across states. Their labor force was massive, healthy, well-fed, and working in facilities untouched by bombing raids. At the height of production, General Electric was building turbochargers at a scale unimaginable to the Luftwaffe. The German engineers examining the P-47 turbo system began compiling a list of what would be required to replicate it. The list grew longer and more hopeless by the hour. Nickel steel for turbine blades, chromium and molybdenum for exhaust pipes, multi-layer heat shielding, high-pressure welding equipment, precision machining tools, uniform cast housings, high-temperature bearings, standardized calibration instruments, thousands of workers trained in mass production techniques. Every line reinforced the same conclusion. The turbo system wasn't simply superior engineering, it was the result of an entire IT. Their labor force was massive, healthy, well-fed, and working in facilities untouched by bombing raids. At the height of production, General Electric was building turbochargers at a scale unimaginable to the Luftwaffe. The German engineers examining the P-47 turbo system began compiling a list of what would be required to replicate it. Germany had brilliant engineers, but brilliance alone was not enough. Their industrial base was shrinking under the pressure of Allied bombing. Skilled labor shortages were growing. Coal shipments were inconsistent. Metal quality was degrading. Even factories capable of precision work were constantly rebuilding after air raids. The Americans, by contrast, were building faster, building larger, and building better every single month of the war. As the German team completed their assessment of the P-47's turbo installations, they turned to the final part of their report. The chief engineer paused before writing the last line. This wasn't a matter of pride, it was a matter of truth. In clear, direct language, he wrote, "The system cannot be reproduced under current wartime conditions, not due to lack of knowledge, but due to lack of industrial capability." This was the heart of the matter. Not that the Americans had invented something mysterious, not that the Germans were incapable of understanding it, but that only a nation with vast resources, stable factories, and unmatched industrial strength could produce such a machine, thousands of times over. The turbocharger of the P-47 was not just a piece of equipment. It was the physical embodiment of American industrial power. And for the first time, the German engineers understood exactly what that meant. When the German engineers finished their weeks-long examination of the P-47's turbocharger system, they gathered in a narrow conference room inside the Luftwaffe Technical Evaluation Center. The table was covered with sketches, metallurgical notes, chemical test results, and photographs of every component they had disassembled. Nearly 24 pages of findings lay stacked in order. Yet the expressions on their faces told a far clearer story than any report. They were confronting an uncomfortable truth. For months, German pilots had complained that the P-47 Thunderbolt climbed too hard, dove too fast, and kept too much power at altitudes where German aircraft began to lose the fight. The Luftwaffe had assumed these claims were exaggerations, excuses from pilots facing overwhelming Allied numbers. But now, with an intact turbocharger open on their workbench, the reason behind the Thunderbolt's high-altitude superiority could no longer be denied. The final report began with technical observations. It documented every major component: the nickel-based turbine blades, the heat-treated housings, the chromium-molybdenum steel ducts, the multi-layer thermal shielding, the near-frictionless bearings, and the precision wastegate system. It included measurements of airflow, temperature tolerances, and pressure retention. And behind each number, behind every technical sentence, lay the same conclusion: this was not a machine the Reich could produce. The head of the engineering team wrote the most important line himself. In dry, formal language, he stated, "Replication of the turbo supercharging system is not feasible within the current industrial capacity of the German Reich." For a country that prided itself on engineering mastery, this was more than an admission. It was a reckoning. The implications reached far beyond manufacturing. If Germany could not build the turbocharger, it meant they could not build a fighter capable of matching the P-47 at high altitudes. And without a high-altitude fighter, they could not stop the growing waves of American B-17s and B-24s that were now crossing into German airspace every week. The turbocharger was not merely a technological advantage. It was the backbone of the U.S. Army Air Force's air strategy. The P-47 Thunderbolt, with its enormous radial engine and advanced turbo system, could escort bombers deeper into Germany than almost any aircraft before it. It could dive on enemies from high altitude with overwhelming momentum. It could sustain power above 25,000 feet, altitudes where the thin air choked German engines and robbed them of horsepower. And perhaps most importantly, it could survive punishment that would destroy other fighters. The turbocharger contributed to all of this by keeping the engine performing at maximum capacity throughout the climb and well into the frigid altitudes of Luftwaffe territory. The Germans, who had once dismissed the Thunderbolt as too bulky, too heavy, and too American in its design philosophy, now saw it in an entirely different light. It was not a brute. It was a masterpiece of industrial balance, firepower, durability, altitude performance, and American production strength working in perfect lockstep. Inside the evaluation center, the engineers debated potential alternatives. Could a simplified version be attempted? Could Germany focus on upgrading its mechanical superchargers instead? Could captured materials be repurposed to build at least a few prototypes? The answers were always the same. Germany lacked the nickel. Germany lacked the chromium. Germany lacked the molybdenum. Germany lacked the welding capacity. Germany lacked the machining tolerances. Germany lacked the industrial stability. And most critically, Germany lacked time. By late 1943 and early 1944, Allied bombing had begun striking German factories with increasing accuracy. Ball-bearing plants, vital for any turbo system, were destroyed. Steel production fluctuated wildly. Skilled labor shortages grew severe. Even if Germany had understood everything about the American turbocharger, building thousands of them was a fantasy. The Luftwaffe engineers understood this better than anyone. So did their superiors. When the report reached senior command, it was not met with anger but resignation. Another path to high-altitude parity had closed. Germany would have to rely on mechanical superchargers and emergency systems like MW-50, water methanol injection, not to surpass the Americans, but merely to survive encounters with them. Meanwhile, in the United States, turbocharger production continued without interruption. American factories built them by the tens of thousands. The GE turbos equipped P-47 Thunderbolts, B-17 Flying Fortresses, and B-24 Liberators, machines that pushed deeper into German airspace with every passing month. The German engineers' final conclusion was stark but accurate. The Americans had won the altitude war, and with altitude came initiative. With initiative came reach. With reach came strategic advantage, and with advantage came victory. The P-47's turbocharger was not the sole reason for America's triumph in the skies, but it was one of the clearest symbols of what separated the two nations by 1943. A massive, unstoppable industrial machine fueled by freedom, resources, manpower, and manufacturing excellence. The Luftwaffe had brilliant minds. The United States had brilliant minds, and the factories to match them. In the end, the Germans did not just learn why they could not copy the turbocharger. They learned what the turbocharger represented: American power, American industry, American dominance in the air, and that realization, quietly recorded in reports and whispered in engineering halls, marked the moment they understood that the war in the skies was slipping beyond their reach.